Hi everybody. So in today's video, we're going to be talking about using an integral to find the area between two curves. Now we're going to do this. We're going to find the area between curves expressed as functions of x and expressed as functions of y. So the idea here is that we're going to have two new pieces of information, the idea that we can find the area between two curves and that we can do this in terms of x or in terms of y, which we'll talk about in a second. What I want to start with right now is a review of an integral as an area. We kind of keep coming back to this idea as we discuss integrals further. The idea here that we need to go back to is the idea that when we find an integral, the integral of a function gives the area between the curve that we've sketched and the x-axis. And the part that I want to really emphasize here is that the x axis is what we always go back to. So it's trapped between two things, the curve and the x axis. For example, if I were to integrate on this graph, the shaded regions here are showing you the areas that we would be finding. And what I want to emphasize here is that in this shaded region, the curve is one of the boundaries and the x-axis is the other boundary. In the middle region, the curve is one of the boundaries of the shaded area and the x-axis is the other boundary. And on the far right side, the curve is one of the shaded area's boundaries as well as the x-axis. So the x-axis is always one of the boundary functions for the areas that we're finding. What's going to be different today is that today we're going to be trying to find the area between one curve and another curve. So instead of using the x-axis as a boundary, we're going to be using another graph as the boundary for our shaded area. For example, in this picture, I'm showing you what it looks like when we have a shaded area trapped between this parabola and this kind of curvy function down here. This shaded region has two boundary functions. The top boundary function is this curve right here, which we would call f of x. And the bottom boundary function would be this kind of wavy curve here. And the area we would be finding would be the area that's in between those two curves. Now, what makes this different than what we've done before is we're not using the x-axis anymore as one of the boundaries for our shaded area. The x-axis is kind of something we're just it's in the middle of the shaded area here. We're not really paying attention to it for this problem. So the question becomes then, how do we use an integral to do this? If an integral normally uses the x-axis as a boundary, how do we use an integral to use a different function as a boundary? So in order to find the area between two curves that are defined in terms of x, so you'll notice that this is f of x and this is g of x. So x is our variable here on the interval from a to b. And I want to emphasize that a to b, these are x values, x1 and x2. So on this graph, it would be a would be here and B would be here. They would be X values. It's kind of like the width of the region from this X to this X. If we want to find that area using an integral, here's how we do that. Normally, when we're using the x-axis as a boundary, we just integrate f of x. In order to use a different function as a boundary, here's how we do that. We do the integral from a to b, and again, those are the starting x and the ending x values. And inside here, we're not going to just put f of x and we're not going to just put g of x. We're going to put f of x, so the top of your shaded region goes first, minus g of x, so the bottom of your shaded region goes second. And your integral would be dx. Now, there's a couple different things I want to really emphasize and point out here about the way we set this up. The top of your shaded region is the first function inside the integral, and the bottom of your shaded region is the second function inside the integral. The other thing I want to point out is that everything here is what we call in terms of x. We have a dx at the end, we have x values as the bounds, and in our equations, the equations use x's as the variables. Now, you might be thinking, well, obviously, that's how we always do things. But what's going to be a little different today is that sometimes instead of integrating with respect to x, we're going to integrate with what's called respect to y. So, what makes this picture different than this picture is that there isn't a clear top and bottom function. In this picture, it's very obvious. The pink function is always the top of the shaded region, and the orange function is always the bottom. What makes this one different is that there really isn't a clear top and bottom. For example, if I were to look at this part of the graph right here, this curve is both the top and the bottom of this slice of the area. So, what makes this different is that sometimes we can integrate with what's called respect to y. What you'll notice is that in these equations, the x is by itself, unlike what we normally see where the y is by itself, and the variable here is a y. So, what I want to point out here is that instead of thinking about things as the top and the bottom, this problem is actually easier if we think about things as the right side of the shaded area and the left side of the shaded area. Now, if we think about this in terms of right and left, the pink function here is always on the right side of the region, and the orange function is always on the left side. So we're kind of thinking about things in terms of slicing it sideways for our shaded region instead of slicing it vertically for our shaded region. You'll notice that I drew this one vertically because there was a top and a bottom for each purple line. Each purple line here has a clear left and a clear right instead of a clear top and bottom. So in this case, when there's a left and a right function, we're going to integrate with respect to y over the interval from c to d. Now you'll notice that I didn't say a to b, I said c to d, because these are actually going to be y values on this graph. C is going to be my lowest y value, and D is going to be my highest y value, sort of the edges, but instead of going from left to right like we did here, it's the edges from top to bottom. The way we're going to set up this integral is going to look like this. We're going to integrate from C to D. So again, I'm using y values here. And inside here, instead of putting the top function minus the bottom function, we're going to do the right function, which in this case would be f of y. I should write this a little like this. F of y, which is the right function, minus the left function, which in this case is g of y. And then instead of putting dx at the end, we're going to put dy. A couple of things that I really want to emphasize here. We wrote dy to indicate that our variables should all be y's. We use y values for our numbers as the bounds of our integral, and our equations are going to be rearranged so that the y is actually what's inside the equation and the x is by itself. All right, we're going to try some example problems, so hang with me here. We're going to start with example 1 by focusing just on finding the area between curves that are expressed as functions of x. So I'm telling you from the get-go, we're going to be doing this in terms of x. It says here, find the area of the region enclosed by the functions f of x equals 2 minus x squared and g of x equals negative x. Step number 1 is going to be to sketch the graph. So I'm going to sketch f of x in pink. There are a couple different ways to sketch this. We could know, for example, that this is going to be a graph that looks like a parabola that's turned upside down, and that's shifted up 2 places, or we could make a table of values. Either way, if you plug in the number 0, for example, you should get 2. If you plug in the number 1, you should get 1. If you plug in the number 2, you should get -2. If you plug in the number -1, you should also get 1. And if you plug in the number -2, you should get -2. Now, this is going to be my f of x function. So this is f of x. And I would highly recommend using different colors here. I think it helps us visualize our graph. Now for g of x, it's going to be the line -x. So it's going to be, if I plug in -1, I get 1. -2, I get 2. -3, I get 3. 0, I get 0. 1, I get -1. 2, -2. And that's going to be my nice straight line. Let me grab a straight edge so I can make a nice straight line. Now I'm going to be asked to find the area of the region enclosed by these two functions. Now enclosed means entirely contained by. So when I look at this graph, I'm going to focus on the area that's here, entirely contained between these two functions. Now if I look at this area, what I notice is that there is a clear top of each slice of the area. If you imagine kind of slicing this, that's why I drew these vertical lines. Each of those slices has a clear top, which is always the pink function, and a clear bottom, which is always the orange function. So because there's a clear top and a clear bottom, I'm going to be integrating with respect to x. So to set up my integral, the first thing I always want to think about is what variable to use. I'm going to set up this integral with respect to x. I'm just going to abbreviate that WRT. It's really important to do that first because that helps me to know what values to use in my integral. So my integral is going to go from my beginning x value, which in this case, the intersection point at the beginning is -1, and it ends at the +2. Inside of the integral, I'm going to think to myself, top minus bottom. In this case, the top function here was 2 minus x squared minus, and the bottom function here is -x. Now I want to be really careful about my notation. The notation here matters. You have to show it the right way. So I'm going to put dx because everything should be with respect to x. Now before I go any further, I'm just going to make sure this has an x, these variables are x's, these are x values, and I did top minus bottom because from here forward, if I made a mistake in my setup, it's going to make my answer totally wrong. So now in order to evaluate this integral, I could do this on my calculator if this was a calculator question, but I do want to review for a second how to do this using antiderivatives. So the first thing that I would do here is I would simplify the integrand, the inside of the integral. So I would have 2 minus x squared, and a minus make plus x, dx. The next thing I would do is I would do the antiderivative. So I would have 2x minus 1/3 x cubed plus 1/2 x squared plus c. And that plus c is kind of optional. We know it's going to cancel out when we start evaluating, but it's not a bad habit to just think of there always being a plus c there. And I'm going to integrate from -1 to 2. I'm going to plug in my top number first. So if I plug in the number 2, I get 4 minus 8/3 plus 2 plus c minus, and if I plug in the -1, I get -2 plus 1/3 plus 1/2 plus c. I know that the c's are going to cancel, and if I simplify what I see here, I'm going to have 4 plus 2 is 6 minus 8/3. Now a -2 times another negative makes +2. I'm going to distribute that negative, so it's +2 minus 1/3, and then I'm going to have minus 1/2. 6 plus 2 is 8. So I have 8, negative 8 thirds, and negative 1 third is negative 9 thirds. So minus 3 minus 1 half, which makes 5 minus a half, which is 4 and a half, or 9 over 2. And I don't care if you write that as 9 over 2 or 4 and a half, but that would be my final answer. The size of that area that I showed you on the graph is 9 over 2 or 4 and a half spaces big. All right, now let's do a problem where we're going to focus on integrating with respect to y. So this says find the area of the region enclosed by the functions x equals y squared and x equals y plus 2. Now, one thing that I think a lot of students struggle with here is how to make these graphs. So I'm going to walk through this a little bit slower than I did in the previous problem. I'm going to graph this guy right here in pink. Now, to do that, I'm going to make a table of values, x and y. Most of the time, what I do when I make these graphs is I choose x values. But because y is the variable here in this equation, I'm going to choose y values. Negative 2, negative 1, 0, 1, and 2. And I'm going to plug them in to get the x's. So if I plug in negative 2, I get 4, 1, 0, 1, and 4. From there, I'm just going to graph the ordered pairs. So 4, negative 2, 1, negative 1, 0, 0, 1, 1, and 4, 2. So this time I'm going to end up with a parabola, but because it's a parabola in terms of y, it's turned sideways. Next, I'm going to graph this second equation, and I'm going to kind of do the same thing you just saw. So I'm going to make an xy table, but just like before, since y is the variable that's inside of the equation part and x is by itself, I'm going to choose y values. So negative 2, negative 1, 0, 1, and 2. If I plug those in, I get 0, 1, 2, 3, and 4. So I would go to 0, negative 2, 1, negative 1, 2, 0, 3, 1, 4, 2. So I would have this line here. You'll notice it looks very similar to the area we saw in the other problem. It's just that it seems like it's sideways. Now, one thing that kind of tells me I'm going to be integrating in terms of y is that if I try to imagine slicing this vertically, some of those vertical slices, I'm going to use the edge of my protractor so I don't muck up my picture, but if I imagine like a vertical slice like this, the top of that vertical slice and the bottom are both on the pink function. We don't want that. We want there to be a top and a bottom. If we look at a slice over here, the top is on the pink and the bottom is on the orange. So again, it changes what's the top and what's the bottom. Sometimes the pink is both the top and the bottom. It just doesn't seem like it's going to work. If we turn our lines sideways and we go from right to left, if we go sideways, the orange is always the right and the pink is always the left. The orange is always the right and the pink is always the left. No matter where we put our slice, the orange is always the right and the pink is always the left. When that happens, it tells you you should be thinking sideways instead of up and down. When I know that I should be thinking sideways, that's what tells me that I should be integrating with respect to y. And it's really important to stop and think about that. There are a couple clues here. Number one, the way the functions are written, x is by itself and y is the variable. Number two, when I look at the picture, it makes more sense to look at my slices going from right to left instead of from top to bottom. So I want to make sure I'm really clear about that we're integrating with respect to y. All right, now we're going to set up our integral. So the way we're going to do this time is a little bit different. When I integrate with respect to y, I'm going to start with the bottom number. Instead of going from like boundaries like this, I'm going to be going boundaries like this. So my area goes from the lowest y value is negative 1 to the highest y value is positive 2. Now inside of my integral, instead of doing top minus bottom, I'm going to do right minus left. So the right side here is actually the orange function. So I probably should have made those the other colors. My bad. So the right side here is actually the orange function, which was y plus 2 minus the left side here is actually the pink function. Man, I really messed up those colors. I apologize. Minus y squared. And I would have d, and I'm going to use the variable y here. Now there are a couple things to check on. You'll notice there's a y here There's y's in all of my equations, and I'm using y values as my bounds. And it's really important to make sure that you're getting those all kind of ironed out, because if you get them mixed up, if you use x's here instead of y's, you're going to get totally wrong answers. All right, I'm going to color over these with black because it's making me crazy that these are the wrong colors. I apologize for messing that up, guys. Okay, so next we're going to evaluate using antiderivatives. And again, you could do this on your calculator. That is a very normal thing. This does tend to be a calculator question. However, I do want to review the process of using antiderivatives because it's been a while and I want to make sure we don't forget. So in order to do the antiderivatives here, I would start by simplifying my integrals. So -1 to 2. Inside of here, I'm going to have y plus 2 minus y squared dy. Not really a big simplification. I'm just getting rid of those parentheses. Next, I'm going to do the antiderivative. So 1/2 y squared plus 2y minus 1/3 y cubed plus c evaluated between -1 and 2. I'm going to plug in my values. So I'm going to get 2 plus 4 minus 8/3 plus c minus, and then I'm going to have 1/2 minus 2 plus 1/3 plus c. My c's cancel. 2 plus 4 is 6 minus 8/3. If I distribute my negative, I have minus a half plus 2 minus 1/3. And if you'll notice, it's the exact same numbers I had up here in my previous problem. So I already know that this is going to simplify to 9/2 or 4.5. Okay. So now that we've kind of worked through a couple examples where we did one with x and we did one with y, what I'd like to talk about next is how do you decide between x and y? So for the next few problems, we're not going to actually do the problems, we're just going to set them up. So if I were to show you an area like this one and I said, would you use x or would you use y? The first thing I want you to notice is that x is the variable in both equations. That's your first clue that x is probably a good idea. The second thing I want you to do is imagine slicing this thing vertically. So if you look at a vertical slice here, f of x is the top, g of x is the bottom. If you look at a vertical slice here, f of x is the top, g of x is the bottom. There's never going to be a time where I slice it vertically and f of x is not the top and g of x is not the bottom. All the slices are the same. F of x is the top, g of x is the bottom. So if I were to set up this integral, I would do this with respect to x. And we can make that decision by looking at the slices, and we can make that decision by looking at the variables in the equations. So I'm going to set up my integral from my first x value, my left side here is from 0 to 4. Inside of here, I'm going to do top minus bottom. My top function is f of x, and that's this guy right here. And my bottom function here is g of x, and that would be this guy right here. And again, I would have dx because my variable here needs to be x. So this is top minus bottom. Now, if I look at the next problem, this is the perfect example of when we would use a y instead. So if I asked you to look at the equations, the first thing you should notice is that the x is by itself and the y is inside the equation, the variable. The second thing you should notice is that if you slice this vertically, sometimes the line is the top and the curve is the bottom, and sometimes the curve is both the top and the bottom. So instead, I think it makes more sense to use the horizontal slices. If I slice this horizontally, you can see that the curve is always the right and the line is always the left. So the right side here is this curve. And even though it doesn't tell me in the directions, I can tell that the curve is this equation because of the y squared. It's going to be curved. And the left side is always the line. And even though it doesn't tell me this in the directions, I can tell that that's this equation because that's the one that doesn't have a power. It's just a line. So if I were to set up this integral, I would integrate from my bottom number, my lowest y, which is -2, to my highest y, which is +1. I should make a note here that I'm integrating with respect to y. And then inside the integral, instead of thinking in terms of top minus bottom, I'm going to think in terms of right minus left. So the right side here would be 3 minus y squared, and the left side here would be y plus 1. And I will put dy at the end because, again, my variable that I'm using here is y. Okay, now sometimes it's not quite as obvious. For example, if I look at this problem right here, one of the equations has x by itself and one of them has y. So just looking at the equations is not giving me enough information to decide if this should be in terms of x or it should be in terms of y, because there's kind of mixing and matching the way they wrote them. Instead, I really have to focus on the slices here. If I think in terms of vertical slices, sometimes the vertical slices go like this: the curve is the top and the curve is the bottom, and sometimes it goes from curve to line. So because of that, I'm going to try horizontal. If I slice this horizontally, the line is always the right and the curve is always the left, no matter where I put that slice. So as soon as I notice that, as soon as I notice I'm going right to left, that's what tells me I'm going to be integrating with respect to y. Now, when I set up my integral, I'm going to start the same way. I'm going to integrate from my lowest y value, which is -1, to my highest y value, which is +2. And inside here, I'm going to put my right function first, which is this line. And this is where it gets a little tricky. I know that this equation is the line because it doesn't have the squared. The squared is going to be the curve. But I need this to be in terms of y. So I'm actually going to need to rearrange this equation to get x by itself, which means I'm going to add 2 to the other side, and I get x equals y plus 2. So in this integral, I'm going to put y plus 2 first. Now I knew I needed to rearrange because I've decided to integrate with respect to y, which means I need to make sure that the y is the variable and the x is alone. Minus, now I'm going to do my left function, which is this curve. Now that's already been arranged nicely for me. The x is already by itself. So I would have y squared here. And then I would have dy. All right, last but not least, in this problem, again, it's a little hard to tell just from the equations. One of the equations has y by itself, one of the equations has x by itself, so I'm going to really need to focus on the slices, whether they go from top to bottom or left to right, in order to make the decision whether to integrate with respect to x or integrate with respect to y. So in this problem, I think it's fairly obvious that the slices make more sense if they go from top to bottom, which means I'm going to integrate with respect to x. So because of that, I'm going to look at my top function first, which is the line, which is this equation right here. Now, just like before, I'm going to need to do a little bit of rearranging here, because if I want to integrate with respect to x, then the y should be by itself. So if I rearrange this equation by adding 2, I get y equals x plus 2. And the bottom of my area here is always this curve, which is the y equals x squared. So when I set up my integral, I would have the integral from my beginning x value, which is -1, to my ending x value, which is +2. And I would put my top function first, which I rearranged to make it x plus 2, minus my bottom function second, which is just x squared. And then I would have dx. All right, we're almost done. And I do apologize that this is a longer video, but obviously not seeing each other in class to go over this, I wanted to make sure I don't rush or go too fast or not be clear about what I'm explaining. All right, so the last idea is that sometimes we're going to have areas of curves that intersect in more than just the beginning and the end. Sometimes they look like this. This is going to be a calculator question, so don't worry, we're not going to be doing antiderivatives here. So the first thing that I would do is I would graph this on my calculator. I just think as soon as it's a calculator question, like, let's do it. So I'm going to go to y equals, I'm going to go ahead and put f of x in my y1, and I like to make a note of which one is where. I just think it's easier. So I would have 14x plus x squared. Oop. And then I would have minus 2x to the third. And I'm going to go ahead and put g of x in my y2. And again, I like to make a note of which one's which. So I'm going to put g of x in my y2, which is going to be x squared minus 4x. I'm going to try to make the graph on my calculator look the same as the graph on my paper. So I'm going to go ahead and change my window. So my window is going to go from -3 to 4. And my y values will go from -20 to 20. And again, I want what's on my screen to match what's on my paper. Now, what I'm noticing about this graph is that there are really two distinct regions I need to find the area of in order to get the total area between these two graphs. So the first thing to do is identify which graph is which. You'll notice I hit trace, and when I hit trace, the little blinky guy is on this curve, which it identifies as 14x plus x squared minus 2x cubed. So on this graph, and I would do this, I would actually mark which one's which. This curve right here, and you could use a highlighter or a pen, is the f of x curve, which we have in our y1 spot. And this curve right here, therefore, must be the g of x curve, which we have in our y2 spot. The next step is to find the intersection points. So I'm going to go ahead and find those intersection points. Right now, I can already um, one mistake that a lot of students make is they assume the intersection points. They go like, oh, it must intersect at -3 and 0 and +3. In this case, that ends up working, but I would never assume that on the AP test. They like to make it look like it intersects somewhere that doesn't really, it's just close. So I would go to second, calculate intersect. And if I wanted to, for example, find this intersection over here, I would just get close to it and hit enter 3 times, and I get that it really does intersect at 3, -3. The intersection point here ends up being 0, 0. And if I go to second, calculate intersect, and I want to be all the way over there, I just need to get close to it. And I hit enter 3 times, and I think it's -3, 21. So the first thing I would do is always actually find the intersection points. I think one of the major mistakes I see a lot with these problems when it comes to AP type questions is people just kind of assume because it looks like it's 3, it's 3, it's not usually. It's usually something close, but not exactly that. The second thing I'm noticing is that okay, we found the intersection points. Step 2 is that because there are two separate areas, we're going to need separate integrals for each section. One of the reasons for this is like in the first section, the orange is the top and the pink is the bottom. And in the second section, the pink is the top and the orange is the bottom. So we can't do this all at once. We need separate integrals. So my first integral would go from -3, which is the first x coordinate of the intersection point, to 0. And by the way, I'm integrating with respect to x here, obviously, because it looks more like it's top minus bottom than right minus left, clearly. So I like to draw those lines in. So in the first region of this graph, the top function is g of x, and the bottom function is f of x. Oop, I'm sorry, it's getting kind of fuzzy as I'm writing. Is f of x. Now, you do not, on my test or on the AP test, need to write out the entire equation when you make these integrals. So just write the g of x and the f of x and be done with it. Plus, the second region here would go from the 0 to the +3. And the top function for this region would be f of x minus the bottom function for this region would be g of x. They switch, which should kind of help you see why we need two separate integrals to make this happen, because it's not the same equations in the same order in both integrals. Last but not least, we're going to type it in. So here's what I'm going to do. When this is why, this is the reason I like to make sure I note which function is in which spot. G of x is in my second spot and f of x is in my first spot. So I'm going to go to math option 9. I'm going to integrate from -3 to 0. Now I'm going to go to variables, y variables, and choose option 2 first, minus variables, y variables, and choose option 1. So for the first integral, it's the second equation minus the first equation, dx, plus, then I'm going to do math 9 from 0 to 3. And now I'm going to go and I'm going to choose the first equation minus the second equation, dx. And I'm going to hit enter. And that's going to give me my final answer, which is 81. Okay, I hope that this video makes sense and finds you well. I hope everyone is staying safe and healthy at home, and I look forward to doing some practice problems. Again, if you need me, send me a quick email and we will arrange a time to talk.